All right, it's 8, so let's get started. Today we are going to continue speaking about the common emitter amplifier. And I will briefly recap what we've done to this point. All right. So we'll start with common emitter core, which is what we dealt with largely in chapter 4. And that's a circuit that looks something like this. All right. And so we found last week, sorry, just a second, that this particular circuit, without the early effect, we had Rn was equal to R pi, R out was equal to RC, and our voltage gain AV was equal to negative GM RC. And if I'm not mistaken, we also went through and figured out what would happen if the early effect were included. And we found that the early effect does not influence the input resistance at all, so it stayed as R pi. It did, however, affect the output resistance. It changed it to RC in parallel with R naught, which in turn influenced our gain equation, which becomes negative GM times RC in parallel with R naught. So what we're going to do today is go through what effects emitter degeneration resistor between the input and the base terminal, which is going to be representative of, say, the Thevenin resistance with our full-size biasing circuit, and then finally move on to our full-size bias or full resistor biasing circuit and see what effects that has and what we can do to kind of mitigate some of the problems that arises because of the way that we bias these circuits typically. So let's move then to the common. Don't know why my pen isn't writing where I want it to. Emitter with degeneration. All right, so with degeneration, this is simply going to look like the exact same circuit, except that we're now going to have some resistance RE between our emitter and ground. So the first thing that we're going to take a look at is determining, we're going to go through all three of the amplifier parameters, the input impedance, the output impedance, and the voltage gain and see what effects this emitter degeneration has on the behavior of the circuit as an amplifier. So if we're looking at our input impedance, we need to look at our small signal model. So I'm going to say, here's my base. Here's R pi, voltage, V pi. Here's my current source, GM, V pi. And we're going to neglect or ignore the early effect. The textbook does it the entire time. Really what all it does is just make the math kind of difficult, and we'll see a way pretty shortly where we can kind of infer what it's going to do. So here's our basic small signal model. Between the emitter and ground, we have a resistor. So we'll put that guy in right here. So here's our resistor RE. Because we are looking for the input impedance, I apply a test voltage, Vx, at my input terminals, measure the current Ix flowing in, and let's see, between the collector and ground, I have that resistance R C. All right, so one thing that I want to point out here is that it may appear that the input resistance is simply R pi in series with RE, but I want to be clear that that is not the case, and it's because the current that flows through the resistor RE is not the same as the current that flows through the resistor R pi. There is another current that's going in there, so we can't make simple assumptions. We need to pay attention to KCL, KVL, and things of that nature. So with that in mind, excuse me, if I apply KVL, I can see that Vx is going to be V pi, the voltage drop over the resistance R pi, plus the voltage drop over the resistance RE. So I can express V pi as R pi times Ix, and I can express the voltage drop over the resistor RE as Ix, because that current flows into that node from B to E, plus GM times V pi, which I know to be R pi times Ix. And so from this, I get Ix divided by R pi plus, let me do a square bracket here actually. So I have GM R pi, so that's beta. So I'm going to have 1 plus beta RE. And from this, I can easily see that my input resistance is now R pi plus 1 plus beta RE. So while we have this fresh in our minds, what effect does the emitter degeneration have on our input resistance? So what's the difference between our input resistance here and our input resistance when we did not have emitter degeneration? Yeah, it went up considerably, right? So RE is typically on the form of 200-ish ohms, thereabouts. We could make it larger or smaller, but typically a little bit less than a kilo ohm seems reasonable. R pi inherently is beta over GM. So that depends on our biasing conditions on this guy, but it would not be unreasonable to have a value of somewhere in the order of a couple of kilo ohms as R pi, right? Because GM is IC divided by VT. So our bias currents that we've been seeing in this guy for our collector, somewhere in the order of a milliamp, usually. A milliamp divided by our thermal voltage. So 0.001 divided by 0.0026. So we get a transconductance of 0.38 beta divided by that, so 100 over. So we get somewhere in the order of a kilo ohm, but 1 plus beta, so that means that we're multiplying RE by a factor of potentially up to close to 100, right? So if we have a 200 ohm resistor, that becomes a 20K ohm increase in our input resistance. That's fairly appreciable, right? It's large in comparison to typical values of R pi. So we can see that emitter degeneration increases our input resistance appreciably, and that's typically a good thing, right? For an ideal amplifier, we want to have an infinite input impedance, and we can see that this causes our input impedance to increase, so we're going to consider this to be a good result. Let's look at what happens with our output impedance. Impedance, there we go. All right. Starting with my small signal model. Let's see, here's R pi, here's V pi, here's GM, V pi. And I put my resistance between my emitter and ground. Because I'm measuring the output impedance, I need to short circuit my input terminals. So I put place a short between the base and ground. Here's my resistance RE. Between the collector and ground, I have my resistance RC, and that's also where I'm going to apply my test voltage of Vx. And here's my current Ix. All right. So any thoughts on what our output resistance may be here? So we can see that Ix is the current flowing into that node, and we can see that some of it should split and flow through that resistor RC, and then the rest of it will flow through that dependent current source GM V pi. That current splits between that resistor R pi and that resistor RE, or at least that's what it looks like what's happening. But if we apply Kirchhoff's voltage law around the left-hand loop again, we can see that the voltage drop V pi plus the voltage drop over our emitter resistor RE. So let's see, the current flowing through that is going to be the sum of V pi over R pi. That's the current flowing this way. Then we take the current flowing in this way, plus GM V pi is equal to 0. What does this tell us about the voltage V pi? It's 0. It has to be 0. Absolutely right. The only way that this mathematical statement can be true is if V pi is equal to 0. If V pi is equal to 0, how much current is being sourced by that dependent current source? None. So no current is flowing through the branch containing the dependent current source. So what's our output resistance? Just RC, absolutely right. All of that current IX flows down through RC because none of it can branch off and flow into the dependent current source. We've mathematically proven that. So from this, we see that R out is exactly equal to RC, which in the case of not having emitter degeneration and not having the early effect, we see that this change to our circuit did not cause an increase or decrease on our output resistance, right? Made no effect whatsoever, which is a good thing. Now, if the early effect were included, it will have some effect. And that's because the resistor from the early effect would be placed, I'm going to draw it in a different color here. Right there. And so we would have some bypass of that current source, right? We know that GM times V pi would still be equal to 0, but we would see that R naught is in series with the parallel combination of R pi and RE. So it messes things up a little bit there. All right, now let's take a look at our voltage gain relationship. All right. So to determine our voltage gain, again, I'm going to start with my small signal model. Here's R pi, V pi, C, here's my emitter resistance RE. Here's ground. So here's my resistance RC, and my small signal output voltage is simply the voltage drop over RC. So let's look back up at our original diagram to make sure that we agree with this statement, right? So small signal model, V out, or large signal, V out is a potential difference between the collector and ground, right? Small signal model, our VCC becomes short circuited. So that's the exact same thing as this voltage, which is the voltage drop over RC. So I just want to be clear about why I'm saying that that is my output voltage. Let's see what we got here. Here's my input. All righty. So let's start with something easy. I can develop a simple relationship for my output voltage right now. It's not going to be related to V in per se, but it will be related to V pi just by using Ohm's law, right? I can say that V out is equal to negative GM V pi times RC. Anybody got any problems with that? The negative sign comes from the fact that the current GM V pi is flowing into the negative polarity terminal of that resistor RC, and then I just multiply that current times RC to get the voltage drop over that resistor, which is my output voltage. So nothing particularly crazy there. I'm going to develop a second relationship with this guy real quick here. So I can say that V pi is then equal to negative V out divided by GM times RC. That's just simple algebraic manipulation. Now I'm going to use Kirchhoff's voltage law around the left-hand loop. And so I get Vn is equal to V pi plus RE times V pi over R pi, that's the current flowing through that resistance R pi, plus GM V pi. So that's the voltage drop over my resistor R pi plus the voltage drop over my resistor RE gives me Vn. Fairly straightforward using Kirchhoff's voltage law. And now I can substitute in my relationship for V pi in terms of the output voltage into here. And what it gets me is Vn is equal to negative V out over GM RC plus, let me write this a different way, RE divided by R pi times negative V out over GM RC plus GM RE times negative V out over GM RC. If I factor out that common factor of negative V out over GM RC, over here I get 1 plus RE over R pi plus GM RE, which looks like negative V out over GM RC times 1 plus 1 over R pi plus GM times RE. All right, and finally then, my output voltage, excuse me, my voltage gain, defined to be V out over Vn is negative GM RC divided by the quantity 1 plus R pi to the minus 1 plus GM times RE. All right, so I'm going to do this in a different color. This is a manipulation on this that we're going to use in a couple of minutes, and so I'm going ahead and going to point it out right now. So since R pi is beta over GM, 1 over R pi is GM over beta, right? So let me write this down. R pi is beta over GM. So if I have the inverse of that, I simply have GM over beta. So inside here, if I multiplied through by R pi over R pi, what this would give me, using this color, is negative beta RC divided by R pi plus 1 plus beta RE. Just expressing the voltage gain of my amplifier in a slightly different form that's going to help us show what an effect is shortly. So looking at this, what effect does emitter degeneration have on our voltage gain? So make it larger, make it smaller, not affected at all? What's going on? Right, so without emitter degeneration, our voltage gain was negative GM times RC. With emitter degeneration, it's negative GM RC over some quantity that's greater than 1 by definition, which means the emitter degeneration serves to reduce the voltage gain of our system. So this is a trade-off, right? It increases the input resistance, which is typically a good thing, but it decreases the voltage gain, which is typically a bad thing for a voltage amplifier. So this degeneration scheme, for the biasing circuitry, we saw that it increased stability. For our amplifier scheme, that increased stability comes at a cost of lowering our voltage gain, all right? We're going to revisit this concept in a little bit and try to figure out if it's possible for us to effectively only degenerate our bias circuitry. And there is a way to do just that. But before we do that, let's explore what happens if we have this exact same circuit, but we include a base resistance as well. Let me see if this is all just people saying they're here. I think it is. Yep. A bunch of people saying. Okay. So common emitter with emitter degeneration and base resistance. So we might have a circuit that looks something like this. All right. So the reason why we're looking at this particular circuit is because we know that in our full biasing scheme, so for instance, I'm going to draw it over here in purple or something like that, right? Apparently I somehow chose white, not purple, that's why. Here is V out, RC, RE, R1, R2, V in. So for a circuit like this, that voltage, or excuse me, that resistance RB is really just representing the Thevenin equivalent resistance of R1 and R2 in parallel for our full-on circuitry, okay? So we need to figure out what exactly having this resistance RB does. All right, so with that in mind, we're gonna have to look at our amplifier parameters and all that kind of stuff again. I would argue, so if we're talking about our input impedance, let's put it here. I would argue that if we drew a line right here, okay, we see is that resistance RB in series with the common emitter with emitter degeneration circuit we just looked at, right? So if we're looking in through this terminal, I'm going to call this guy Rn prime. We know exactly what that is. We just calculated it a few minutes ago. It's R pi plus 1 plus beta Re. So if we look in through this terminal, what do we see? Well, we just see RB plus Rn prime, okay? So we don't have to draw our small signal model again and do all of that analysis if we can break these things up into building blocks that we know how each individual part behaves. This is where our qualitative analysis really starts to kick in to help simplify things, okay? So by inspection, really, I can see that my input impedance, Rn, is Rb plus Rn prime is simply Rb plus R pi plus 1 plus beta Re. No real troubling circuit analysis or anything like that for us to deal with, okay? Nothing too wild there. Excuse me. How is our output impedance going to behave? So I'm going to scroll up here and we're going to revisit our drawing for output impedance when we didn't have that base resistor in, okay? So including the base resistor now, where would that go in this circuit diagram? Yeah, where would we place RB in this circuit? In series with R pi, absolutely right. So it would be something like this, right? It'd be between B, the base terminal, and ground because we have to short out our input voltage. How would this influence this Kirchhoff's voltage law equation? Well, we would have RB multiplied by V pi over R pi plus, oops, second time I dropped this thing, all this other stuff. Does that change the value that we get for V pi at all? No, it's still 0, which means this base resistance does not have any effect whatsoever on our output resistance. And so we can see easily that R out is still equal to RC. For our voltage gain, I'm going to define a voltage here, VB, okay? And I'll explain why I'm doing this, but effectively I'm looking at this amplifier in 2 stages, okay? The right-hand stage is simply the common emitter amplifier with emitter degeneration that we've already analyzed and we already know how it works. And then I have this other stage out front that really all it's doing is attenuating that voltage Vn, right? By definition, if there is current flowing through that resistor RB, then VB is going to be smaller than Vn. I just need to figure out that relationship. So my overall goal here is I'm going to say that my voltage gain is V out divided by VB, which is a relationship we know, multiplied by VB over Vn, right? So if I can get these 2 transfer functions effectively and multiply them together, it tells me what the voltage gain of the whole system is. Well, I know that V out over VB, excuse me, is just this voltage gain. Nothing changed at all. So I'm going to write that as negative beta RC divided by R pi plus 1 plus beta RE. Let me make sure I copied that down correctly. 1 plus beta RE, yes, all right. Now let's talk about how we're gonna figure out what the transfer relationship VB over Vn is. So from the perspective of our input voltage, it sees some resistance RB. Here is my voltage VB. And then it sees the input resistance of my common emitter stage with emitter degeneration, which would be R pi in series with 1 plus beta RE. Anybody got any problems with that? That's literally how we found the input impedance of this thing a minute ago, right? It doesn't care about what's going on at the output. This is what it sees. It's simply the resistance RB in series with the input resistance of that amplifier stage. So I can figure out what VB over Vn is just using simple voltage division rules, right? So VB over Vn is just going to be the total resistance seen between VB and ground, or R pi plus 1 plus beta RE, divided by the total series resistance seen at the input, RB plus R pi plus 1 plus beta RE. Anybody have any questions where I got that relationship from? Just using the voltage division rules, right? So VB is equal to that ratio of resistors multiplied by Vn, and then I just divided both sides by Vn. So from this, my voltage gain is, let's see, R pi plus 1 plus beta RE divided by RB plus R pi plus 1 plus beta RE multiplied by negative GMRC over R pi plus 1 plus beta RE. Those two guys cancel each other out, and I'm left with negative GMRC over RB plus R pi plus 1 plus beta RE. So what effect does including that base resistance have on our voltage gain? So this guy right here is the voltage gain for the common emitter with emitter degeneration, but without the base resistance, right? So all it's doing is just adding RB to the denominator. So it's making it smaller, but it may not be appreciably smaller depending on what that value is. So it's lowering the voltage gain overall from our degenerated state, but it's not nearly, the effects of this are not nearly as large as the degeneration itself, because that resistor value was multiplied by a factor of 1 plus beta, right? So we can get a large resistance there. All right, so we got 30 minutes left. Okay. So let's cycle back around to what we talked about a couple of minutes ago. How can we degenerate only, or get emitter degeneration only on the bias stage, but not on the amplification stage, okay? So if we looked at common emitter with a full bias circuit. So let's say now that we're looking at this guy. Here is our collector resistance. For now, this is going to be V out, and we'll talk about what I mean for now in a second. Here's our emitter resistance. And then here, I have that resistor R1. Here's that resistor R2. And then for now, this is going to be Vn. Okay? So if we want to have, oh, and this voltage here is VCC. So if we want to have the degeneration occurring in the biasing, but not in the small signal analysis or in the amplification, what does that imply? So the biasing circuit is it a DC circuit or an AC circuit? So if VN, if we did not put some sinusoidal or whatever input signal there, would this be a DC circuit or an AC circuit? It's a DC, okay, right. It's a DC circuit. So we want that resistor RE to be in there for DC circuits, and we want it to be removed for AC circuits. So that means we're going to need to place something in parallel with it that's going to look like a short circuit at higher frequencies, right? Or to our AC signal. Anybody have any thoughts on what that might be? So it's going to need to look like an open circuit to DC and a short circuit to AC. I feel like you should too. So circuits 1 question. Pardon? Speak up. A capacitor, absolutely right. C, E, yeah. So what that capacitor does, and it has to be sized large enough such that, okay, so ZCE needs to be much smaller than RE at our frequency of interest. All right. If it isn't, then we just have 2 impedances in parallel, and so we make our relationship that we had previously complex in nature, which is going to be a total pain in the butt. But if the impedance of our capacitor is very small in comparison to that resistor RE, it just looks like a short circuit, right? Which is going to keep our degeneration for our biasing circuitry, but remove the degeneration, so removing that voltage gain reduction that we saw in our small signal model. Another couple of things that we might do is, instead of just having that purely there, we might put a capacitor here. And just for the sake of argument, I'm going to say that we might have some basance there as well, where this guy is being. So let's talk about that base resistance first, okay? So that base resistance is really what we would consider the internal resistance of whatever our input signal generator is, right? So if we had, say, a microphone or something like that, like if we were trying to build a simple amplifier circuit to take an electrical signal from the output of a microphone and boost it so that we could play it through speakers, this is what we would be looking at, all right? That signal generator, the microphone in this case, has some internal resistance that needs to be accounted for. What that capacitor CB does is it isolates the signal of the microphone or whatever our sensor is from influencing the bias point of our circuit, right? So when we're doing our DC large signal calculations, that's an open circuit there, and we don't see that AC input signal causing our operating point to fluctuate. And so that's what's called capacitive coupling. It's only passing the AC signal through. And again, we need to size CB such that it looks small in comparison to the remaining resistors so that it looks like a short circuit. Now, if we load this guy, right? So we want to put some load on it. We'll also put a load capacitance. Here's our load resistance. So this might represent a loudspeaker. And here's where we would take our true output voltage of our system. That capacitor, then what it's doing is it's taking away the DC component of our output so that we only see the AC component at our output because it would behave as a short circuit. So can we use the knowledge that we've gained on how the common emitter amplifier works to analyze this significantly more complex circuit as an amplifier without really increasing the punishment of it, I guess, or how difficult this is? Any thoughts? It looks way worse. Okay, I definitely agree with that. It looks way worse. So let's redraw it so where it doesn't look as bad. So let's call this representation a simplified small signal circuit. All right, so for our small signal circuit, we are going to consider all of our capacitors as short circuits. We are going to assume that we've chosen them large enough so that at our frequency of interest, they represent close to zero impedance, okay? So that means we're going to have something that looks like this. We have our input voltage. We have that base resistance. All right. So what happens, small signal model, with the resistors R1 and R2? If we zero out VCC, what's the relationship between R1 and R2? How are they connected? So if, let me do it so the people on Zoom can see too. We're looking at this node right here, okay? If VCC is now 0 volts because we're at a small signal model, then that resistor R2 is between that node I've circled and ground, and that resistor R1 is between that node I've circled and ground. How are those two resistors connected? They are in parallel. All right. Now I have my transistor. Because I'm assuming that my capacitors are short circuits, I do not have emitter degeneration anymore, and so my emitter is effectively shorted to ground. Here's my output voltage. All right, so what's going on with our resistors RC and RL? So let me throw a circle around this node, right? So for our small signal model, the resistance RC is between that node I've circled in blue and ground, right? Because VCC is 0 volts. and the resistance RL is between that node I've circled in blue and ground. So that means that those two resistors are simply in parallel with each other. So, do we know how to analyze this? I would argue that if we split it up, recognizing that this guy right here is VB, the answer is yes. Because it looks like a common emitter amplifier, except that now we have two resistors in parallel as RC, our output resistance, in series with just some voltage divider network, which would be pretty trivial to figure out. Anybody got any thoughts, comments, concerns about looking at the circuit in that way? All right. So let's figure out what our input impedance is going to be. Here I have my voltage Vn, RB. Here's R1 in parallel with R2. This is my node point where I have a voltage VB. And connected to the right-hand side of that node VB is going to be what? So what do I see when I'm looking in through that input terminal? Just that resistance Rn prime, right? Okay, so for this circuit, what is some garbage? Rn prime. Look back through your notes. What kind of circuit is this? Where's an RE? Or what's RE in this case? I got no problem with using that if you can tell me what RE is. It's 0, which means it's just R pi, right? So if we're looking in through this terminal and trying to find the overall input resistance of this scheme, we have going to be RB plus R1 in parallel with R2 in parallel with R pi. Anybody have any problem with that? Pretty easy, right? For our output impedance, we're looking in through our output terminal where Vn is shorted. So what should we expect this to be based on our prior knowledge of how these common emitter circuits work? So I would argue here that from the output terminal, we would see that RB is in parallel with R1 in parallel with R2, right? If we ground our input terminal, then that puts RB in parallel with R1 and R2, which means it'll just look like a smaller base resistance for this example, right? where we saw that the presence of a base resistance did not influence our output resistance at all. So I will ask again, what do we see as our output resistance then? Yep, that's it. Because we know that everything, the transistor and everything to the left is separated by effectively an open circuit. So that we have no path for current to flow, so none of it matters. So RC in parallel with RL. Lastly, we need our voltage gain. So we're going to approach this in much the same way as we approached our last scheme where we just had a simple base resistance in series with our common emitter core, meaning that we can look at everything to the right as simply a common emitter amplifier that we know how it behaves, and then recognize that VB is just an attenuated version of our input voltage VN because it's being applied to a resistor network. Anybody got any problem with that? All right. So we're going to have the exact same relationship. AV is equal to V out divided by VB multiplied by VB divided by VN. Do we know inherently what either of these two relationships are? So V out over VB or VB over VN. Any thoughts? Yeah, so V out over VB will be the same thing as we had earlier, but what earlier case are we talking about here, just to be very specific? So we don't have degeneration, emitter degeneration, because that resistance is zero, right? So this just looks like a common emitter core, right? If we ignore everything to the left of that dashed line and just treat that as some voltage VB, we just have a common emitter core amplifier, no degeneration, nothing remotely fancy about it, right? The only thing is that we have R out is equal to RL in parallel with RC. So for your base common emitter amplifier, what is the voltage gain of that circuit? Negative GM times R out. Exactly right. So we know that V out over VB is negative GM RC in parallel with RL by inspection and using our prior knowledge. How are we going to figure out what our VB over VN relationship is? The same way we did it earlier, right? So we can actually use this drawing from our input impedance relationship to figure out what it's going to be. So how can I use voltage division to figure out what VB is in this case? All right. You junior electrical engineering majors, do you possess the capabilities to analyze this circuit? Yes. How is that circuit any different than that circuit? It isn't, all right? So I would argue, let's call this guy R1, R2, and R3. Vx is going to be Vs times R2 in parallel with R3 over R1 plus R2 in parallel with R3. Anybody have any problem with that? We'll do the exact same thing. All right. So VB over Vn is going to be R1 in parallel with R2 in parallel with R pi divided by RB, which is plus R1 in parallel with R2 in parallel with R pi. If I multiply these two results together, what I get is negative GM RC in parallel with RL multiplied by R1 in parallel with R2 in parallel with R pi. All of this is divided by RB plus R1 in parallel with R2 in parallel with R pi. Thoughts? Anything, anybody see anything incorrect with this? All right. So you now have the means by which to design a common emitter amplifier for a particular load resistance, all that kind of good stuff. You know what the gain is going to be. So like in your homework problems, for example, the web work problem, let me look at this guy. Keyboard thing will start working. The impedance of them, right? So if you had a signal at a particular frequency, the impedance is simply 1 over j omega c, right? You want the impedance of that capacitor to be small in comparison. So let's circle back there real quick. I believe in the homeworks, anytime it has a capacitor, it just says assume it's really large, which means that for even lower frequencies, it would be treated as if it were a short circuit. But let's, where's the thing? There we go. Yeah. So we said specifically that we want the impedance of the emitter capacitance to be smaller than, significantly smaller than the emitter resistance. We want the impedance of the load capacitance, excuse me, to be very small in comparison with the load resistance. And we want the base capacitance to be very small in comparison to the base resistance. We're putting, these other guys are in series so that they just look like short circuits. This guy is in parallel specifically to short out that emitter degeneration resistor so that we get the effects of it in our biasing circuit, but we don't see the effects of it in our amplifier circuit. Okay, is that clear? All right. Excuse me. So Homework, oh, I need to open this thing up. Homework 7, problem 1. This is the only one on a common emitter amplifier. So, we did not cover technically how to analyze this particular biasing scheme because we made it harder and put other resistors and crap like that in. So it should be fairly straightforward to figure out what the bias point of this guy is, or at least develop an equation for the bias point. The reason why I say that is we're told we have a degenerated stage here. It is a common emitter amplifier because the input is applied at the base and the output is taken at the collector, so it's a common emitter. It does have emitter degeneration because an resistor R2 is placed between the emitter and ground. We are told that we want a voltage gain of 10. They mean voltage gain magnitude of 10 because as we saw, common emitter amplifiers always have a negative voltage gain. So don't stress yourself out trying to figure out how the hell am I supposed to make it positive 10. You're not. It's supposed to be. The magnitude of the voltage gain is 10. And you're told that it's operating at the edge of saturation, which is going to help you develop your equation. So for instance, for this particular circuit, and we are, since it's at the edge of saturation, we can easily say that we're neglecting the early effect, and we didn't cover early effect with degeneration. If we look back here, that circuit looks like this circuit, right? So we have multiple different representations, all well-defined for what the voltage gain is supposed to be. We know what beta is. R pi is beta over GM. We don't know what GM is, but GM is based on the operating point conditions, right? GM inherently is IC divided by VT. So this is an equation which is going to relate a known quantity to two unknown parameters, IC through either R pi or GM, depending on which way you want to look at this, as well as that unknown resistance RC. Fairly straightforward. The other relationship we're going to have to get is using the DC analysis of the circuit, where since we are at the edge of saturation, VBE is exactly equal to VCE. So we could say that VBE is equal to VCC minus IC times RC minus 1 plus beta times R2, where the only things we don't know in that equation are also IC and RC. So we have two equations and two unknowns, IC and RC, and we should be good to go to calculate all the operating point conditions and then calculate the input resistance of this guy, which should just be R pi plus 1 plus beta RE, and R pi is dependent on IC. So fairly straightforward there. The next couple of circuits are common base circuits, I think, which is what we're going to talk about on Wednesday. So, so for right now, problem 1 is the only homework problem you should be able to do, but problems 2 and 3 shouldn't be too difficult. We've beat the common emitter amplifier straight to death. We're going to go a bit quicker on the common base amplifier because we know how to figure out input resistance, output resistance, voltage gain, and all that kind of stuff. And it's going to turn out that it's going to be a little bit easier to do a couple of things as well. So I'll see you guys on Wednesday. Yes, sir. I need to talk to Dr. Batari about that, but my best guess is no, because there's no way I'm going to finish. So we have common base and then common collector to do. Those are going to take 1 day each, then we'll be ready for the test. So my best guess is it's going to be Monday night, because that'll give us time to grade it and all that jazz before the drop date, which is in a week from this Friday.